All right. So what we want to do now is look at our logistic model and kind of figure out some of its characteristics. We want to analyze it a little bit more. And looking at these two guys right here, these are typically the types of curves that we're looking at with a logistic model. Because in most cases, you don't start with a population size that exceeds your carrying capacity. That would require some kind of intervention. Like I said in the last video, somebody transplanting an oversized population into a larger or into an environment with a smaller carrying capacity. Most cases, we're looking at a curve like this. So we did say a couple of things. First of all, 0 is a repeller, K is an attractor. Notice that both of these curves are increasing curves. They're monotonically increasing, and that's to be expected because, again, the population is expected to be growing, approaching this carrying capacity of K. It would take some other kind of factor to cause this to decrease at some point in time for some unknown reason before getting here. So they're increasing functions. But then look at both cases. There seems to be a change in concavity in both of these functions. In fact, that's where this K over 2 comes into play. In both of these curves, it appears that the function or the curve is concave up until we get past this K over 2 here, and then it starts to become concave down. Now, what does that really mean? Well, if a curve is concave up the way that we're seeing it here, that means that its rate of change is increasing. If you drew a bunch of tangent lines to this part of the curve where it's concave up, you're going to see that they're gradually increasing in slope until we get here. So, faster and faster rate of growth until we get here. Once we hit K over 2, you're starting to see the rate of growth slow down. It becomes concave down, and those tangent lines start to become less and less steep. Okay? So that leads us to this hypothesis. Again, we're just looking at a picture and trusting our gut with it. We haven't shown anything explicitly. But that leads us to a hypothesis that in a logistic growth model, the population growth rate is maximized when the growth rate is half of the carrying capacity of that environment. So that seems to be the case. We would like to show that that's the case using our model directly. It also looks like there's a change in concavity where the point that has K over 2 as its value of P acts as a point of inflection, and we're concave up before that, concave down after that. I'd like to show all of that stuff here. Okay, so once again, suppose we're working with a population that has a carrying capacity of K, an initial population size of P naught that's between 0 and K, meaning we're looking at one of these two cases. I would like to show that this model maximizes its growth rate when P is equal to K over 2. And then I have some other stuff I want to show too, but let's start with that. So let's first remind ourselves of what our logistic model actually looked like. It's Kp times 1 minus P over the constant K, capital K, that's lowercase k. All right, this is my growth rate, right? And if I want to maximize this is an optimization problem. I look for a critical number, like I would in a Calculus 1 class, by differentiating this and setting it equal to 0, right? So let's differentiate this. If I did that, I'm going to have that actually gives me the second derivative of P with respect to T. And on this side, we're differentiating with respect to T, which means I'm doing implicit differentiation here because there are no explicit functions of T showing up. I have P's here. And I'm also seeing the necessity for the product rule. It's a function of P times a function of P. So using implicit differentiation, that's going to look like K dP dt times 1 minus P over K, derivative of the first times the second, plus the derivative of the second times the first. So Kp times the derivative of this guy, which would be negative dP dt. Okay, let's simplify this. I see a K and a dP dt in both cases that can be factored out. That's going to lead to this K times dP dt times 1 minus P over K, and then I have a negative P left over here, so that becomes I'm sorry, I messed up my I messed up my derivative. This derivative right here is not just negative dp dt. I have this constant of 1 over k here, so it's actually over capital K. I accidentally left that off. So if I factor this guy out and this guy out, I'm left with negative p over k there as well. Negative p over k. Okay? I can simplify that, but in addition to that, dp dt, the dp dt that's showing up here, I have an equivalent expression for that in terms of just p's given by my differential equation here. So let's substitute this in for that. This k and this k are the same, so that means I have a k squared, p times 1 minus p over k, and then this simplifies to 1 minus 2p over k. Okay? Now if that's equal to 0, remember I set that equal to 0 because I'm looking for a critical number. I can then solve this thing. That implies that p is either equal to 0, that's from this factor right here. P is equal to, what would cause this expression here to equal 0? Well, p would have to equal k, because that's 1 minus 1, so p equals k. Or 1 minus 2p over k equals 0, which would imply that p, if you solve this, is equal to k over 2. Okay? Now look at these three cases here. P can't equal 0 and it can't equal k. These are equilibrium solutions. We found that already, right? So as equilibrium solutions, these things act as horizontal asymptotes. P is not going to get there. So this is the only critical number that actually makes sense for a point that would be on our curve. And you can verify pretty easily that this critical number gives you a maximum as opposed to a minimum. So this establishes the first thing that we wanted to show. This is our critical number, and it gives us a maximum rate of change in this function, but this function represents, a maximum value for this function, which represents our rate of change in our population with respect to time. What else do we need to do? We need to show that our solution curve, so either of these two blue curves, has a point of inflection at that point where p is equal to k over 2. Okay? And remember, to check and see if something is a point of inflection, you need to find, first of all, where your second derivative is equal to 0. We just did that, right? Here's our second derivative of p with respect to t, and we found the values for which it's equal to 0, and we determined that these two values don't actually show up anywhere on the curve because they're asymptotes. So this is the only thing worth mentioning. And you need to also show that you have a change in concavity as t increases past that point, right? So we're going to use the fact that this is an increasing function. Since p of t is increasing, then p increases as t increases, okay? We're going to use that so that we can show that we have this change in concavity here without having to get, by basically being able to talk it out. So here's what I mean by that. Let's suppose that we're tracing a point along this curve, and we're looking at values of t that are smaller than whatever value of t gets me this point right here, my point of inflection, right? So we're looking at values of t that are less than this value of t with a corresponding p-value of k over 2. So if t is less than that, then by this assumption down here, that this fact that p is an increasing function, we know that p would also be less than k over 2 in that case. So I want to investigate the concavity of this function. Now here, my second derivative, after simplifying, it came out to this. And I want to consider what would happen if p is less than k over 2. Well, it's a positive number, so k squared times p would be positive. In addition, if it's less than k over 2, then it's also less than k, which makes this a proper fraction, making this positive. So we have positive times positive. If p is less than k over 2, then this entire fraction right here will come out to be less than 1, and you can verify that. Okay, so this is positive as well. Everything is positive, so my second derivative is positive, which means our curve should be concave up from here to here. That's basically what talking that out determined. What happens as p exceeds k over 2? In other words, if p is between k over 2 and k. Well, you should see without too much trouble that both of these factors will still remain positive, but this one, this term right here becomes larger than 1, which makes this term negative. So the whole thing goes negative, giving me concave down there, okay? Now, I did here, I just want to point something out. I said that the function is increasing, but I'm only using the picture here to make that determination. How do I actually know that the function is increasing? Well, we go back to what our solution for this DE was, for this growth model. So our solution that we ended up finding, where's my page where I had that? Our solution ended up looking like this. P of t equals our carrying capacity k over 1 plus a e to the negative kt. The way that we derived a, it would have to be a positive number. We know that for sure. So with that said, how do I know that this is an increasing function? Well, think about what happens as t gets larger, okay? As t gets larger, I have e to a negative kt. K is positive, t is positive. Putting this minus out here makes that negative, okay? What happens when you take e to a negative variable power? That's a decreasing function. E to this is a decreasing function, which means this entire denominator is a decreasing function. You can see that without too much trouble. But as the denominator gets smaller, the whole rational expression will get larger. Notice that my numerator is a k. It doesn't depend on t. So that, talking it out that way, you can see that this should be an increasing function, right? That justifies this assumption that we made up here. There's one more thing that we wanted to mention, which was the limiting behavior of this logistic model. In other words, we want to look at the limit as t goes to negative infinity of our function. So as we go backward in time, what happens to our population? And as t goes to positive infinity of our function. As we go forward in time, what's happening? Well, the curves make it pretty clear what should be happening there. As we go backward in time, our curve is approaching 0. And as we go forward in time, our curve is approaching our carrying capacity, as you would expect. But is that consistent with our solution? Well, let's see. What's happening as t approaches negative infinity here? Well, now t is being allowed to go back in time, so t is allowed to be negative, and we get a negative number that's very, very far from 0. Now this makes negative k times a very large in absolute value negative number, giving me a very, very large positive exponent on that e. So that means this term, as t approaches negative infinity, this ae to the negative kt is going to get extremely, extremely large very quickly, moving backward in time. But that means we have a very, very large denominator with a very relatively small numerator, which means this entire thing is going to shrink to 0. That confirms the suspicion that we had by looking at those solution curves. What about if t is allowed to go to infinity? Well, the difference here is that this negative k times positive large t is going to be a very, very large negative exponent, right? Because we have negative k times positive t. So this becomes very, very large in absolute value, but negative. That means that this entire term is going to become very, very small because the fact that the exponent is negative, shrinking ultimately to 0 in the limiting case. So as this shrinks to 0, this entire expression is shrinking to k over 1, or just k. Okay, so that's the limiting behavior of this function. It confirms what we expected both from our intuition regarding population growth and the curves that we are seeing up here. So to wrap up this section, I'd like to do an example where we have to use the logistic model. Okay, here's what we know. There's initially 1,000 deer in a mountain range with a carrying capacity of 10,000. After 1 year, the population grows to 2,500. What will the population be after 3 years, and at what point in time will the growth rate of the population be maximized? Okay, so we're assuming a logistic model for population growth here. And rather than go through and set up the differential equation and solve it, we've already done that. We've already come up with a solution to the logistic model in the general case. So let's just use that solution, okay? In this case, P of t is going to equal our carrying capacity, which we're told is 10,000, over 1 plus, now A, remember I need that A here, but what was A equal to? We said that A, when we derived it, was equal to our carrying capacity K minus our initial population divided by our initial population. In this case, our carrying capacity is 10,000. We're told that our initial population is 1,000 over 1,000. That's 9,000 over 1,000, which is 9. Okay, so that goes up here. 9 e to the negative kt. Okay, and we don't know what k is. We haven't figured out k. But we can, because we have an initial condition to work with also. We're told that after 1 year, P of 1, our population grows to a size of 2,500. I would like to use this to eliminate that unknown constant there so we have a usable function. Okay? So to do that, let's use that initial condition down here, initial condition. That will look like this. 2,500 equals 10,000 over 1 plus 9. I'm plugging a 1 in, so this becomes e to the negative k there. Okay, divide both sides by 10,000. I get 1/4 after simplifying equals 1 over 1 plus 9 e to the negative k. Take reciprocals. 4 equals 1 plus 9 e to the negative k. Subtract 1 to get a 3. Divide both sides by 9 to get 1/3 equals e to the negative k. Now, as was the case back in 3.1, I am not going to solve for k. I'm going to let this just stay in the form of e to the negative k. Because what does that mean? Well, that means that e to the negative kt, which is showing up in my solution up here, is equal to e to the negative k to the power of t, which according to this is the same thing as 1/3 to the power of t. Now I can rewrite my solution in a more usable form. So I have P of t equals 10,000 over 1 plus 9 times 1/3 to the power of t. Okay? So what do we need? We were asked two questions. What will the population be after 3 years? That's the same thing as P of 3, which in our case equals 10,000 over 1 plus 9 times 1/3 to the power of 3, 1/3 cubed. Okay? This you can actually do by hand if you know what you're doing. 9 is the same thing as 3 squared. So 3 squared times 1/3 cubed is the same thing as 1/3. Plus 1 would be 4/3. You know, take the reciprocal of that and multiply to 10,000. That's 3/4 times 10,000. 3/4 of 10,000 is 7,500. You can also just put it in a calculator. You don't have to do the mental math if you don't want. So that means we have, after 3 years, 7,500 deer. I should write deer. Okay? Or at least that's what's predicted by the model. We know it's not going to be perfect. What's the other thing that we were asked to find? At what point in time will the growth rate of the population be maximized? Well, we already did the work to determine that the growth rate is maximized when your population is exactly half of your carrying capacity. So if our carrying capacity is 10,000, then what we're looking at is a population of 5,000. But at what point in time does that occur? Let's make a guess, and then let's see if our guess is correct. So after 1 year, we have 2,500 deer. And after 3 years, we have 7,500 deer. That's what we just found down here. Half of our carrying capacity is 5,000 deer, right? Our carrying capacity was 10,000. Half of that is 5,000. That's exactly between 2,500 and 7,500, okay? But what population size is exactly between, or sorry, what time is exactly between 1 year and 3 years? We average them. That would be 2. So it would kind of make sense if after 2 years we've reached that halfway point for our population size, which is where your population growth will be maximized. But this is also not a linear function, so we can't necessarily assume that. Let's find that directly and see if our hypothesis is correct. I need to figure out at what time my population will reach a size of 5,000 now, half my carrying capacity. So I set that equal to 5,000. 1 plus 9, 1/3 to the t. This is the same thing as 1/2 equals 1 over, I'm dividing both sides by 10,000 here, 9 to the 1/3 to the power of t. Take reciprocals. 2 is equal to 1 plus 9 to the 1/3, or 9 times 1/3 to the power of t. Subtract 1, that gives me a 1 here. Then divide both sides by 9. I get 1/9 equals 1/3 to the power of t. You can solve this with a logarithm, but you don't have to. It's easy enough to see that 1/9 is the same thing as 1/3 squared. That would imply that t is, in fact, equal to 2, like we suspected. 2 years. Okay? We couldn't just stop with our initial assumption, or our initial observation that 2 is the average of 1 and 3, because that's more thinking of our function as a linear function, but this turns out to still be the answer, 2 years. Okay, that's it for section 3.2.